Welcome back to the second episode of our non-smooth optimization lecture series. If you're new here on this channel, then I strongly encourage you to subscribe to the channel, right, and join our community of simple-minded mathematicians. So today we are going to talk about differential calculus in Banach spaces, right? So the goal actually, or the idea here is basically to extend the classical notion of derivative that you know in finite dimensional cases, right, to Banach spaces, right? We want to extend it to infinite dimensional spaces. Well, why should we care at all, right? I mean, you might wonder. So, say you want to minimize the function f defined on a subset U of a Banach space, right, into R. So say you want to find, minimizer of this function, right, over U in U. Right. Maybe I should put an interrogation mark. Okay. So if this Banach space S X, right, is equal to RG, right, if you have this finite dimensional space, right, so if X equal to RG and your function is differentiable, then life is easy, right? Then life is easy somehow. Because, basically for the existence of the minimizer, right, if you want to prove the existence, because the existence we actually follow from the fact that, if U is compact, right, compact in finite dimensional case is equivalent to closeness and boundedness. Close plus bounded. Right? Then the existence actually follows by the Weierstrass theorem, or Weierstrass theorem. That's how the German will say it. So the existence, then existence follows by Weierstrass theorem, right? Because this is what you know already, right? And also the optimality condition, right? So the optimality condition in this case, the optimality condition, will be what you know already, but we know it basically under the name of Fermat principle, right? If you have a minimizer of a functional, then the derivative, right, or the gradient, right, depending on the space, right, dimension of the function at that point should vanish, right? So the optimality condition follows by the Fermat principle. So if U is open, right, if U is open, then the optimality condition would be the gradient of f at the minimizer, U bar, should be 0, right? And if U is not convex, it's not open, but rather convex, then the optimality condition, you can prove this, that the optimality condition is given by the gradient of f at U bar, right? This would be the scalar product, right? With U minus U bar is less or equal than 0 for every U in U, right? You can put transpose here, depending on how you define vectors in RG, right? So it's up to you. So, basically this is how one would characterize minimizer of such a functional, right, in finite dimensional case. Everything is quite nice, right, when dealing with finite dimensional smooth minimization. So, but the problem is that, in order to characterize minimizers of functionals on infinite dimensional setting, right, when this X here is not a finite dimensional space, right, we would like to, in fact, we would like to characterize minimizers, right, still via the Fermat principle, right? But in the case where X is actually infinite dimensional. So we need somehow to transfer this notion of the gradient, So we need to transfer this notion of the gradient here, to the infinite dimensional space, right? Because this actually, doesn't have any meaning, right? In infinite dimensional setting. So you need to transfer what do we mean by derivative in infinite dimensional spaces. So this is basically, so you just need to, as I said, to transfer the classical derivative concept to Banach spaces. So this is done, in the following way. Say now you have a couple of definitions. So let X and Y be Banach spaces, right? Infinite dimensional Banach spaces, right? Otherwise, you can just use the classical notion of derivative that you know from finite dimensional setting, right? From the lecture on differential calculus, for instance. So let X and Y be Banach spaces, right? Say you have a function f, right, defined from X into Y, right? Be a mapping, and let X and H, right, be element of X, right, be given. So the first definition would be the directional derivative of f. So if you put it in color, so if the one-sided limit say I call it f frame, right, of x comma h, right, which is defined as being the limit of f of x plus th, right, minus f of x divided by t. So the limit when t actually approaches 0 from above, right? When t goes to 0, people will say 0 plus, right? So if this one-sided limit actually exists, so maybe just need to shift it a bit. Or maybe, so if this one-sided limit exists, right, saying that this is in y, right, it is called the directional derivative. The directional derivative of f in x, right, and in the direction h. Good. So this is how, one will define the directional derivative of a function f on Banach spaces. So you can see that it looks quite similar to what you know, right, from finite dimensional setting. So the second definition will be that if the directional derivative exists, right, if f prime of x h exists, right, for all direction h in x, right, and that the map that we call dfx, right, defined from x to y, right, if this map actually defines the bounded linear operator, right, so this means that gf x is actually in capital L of x comma y. This is actually the space of linear bounded operator from x to y. So if this map is actually bounded and linear, right, Then we call sorry, then we call f Gâteaux differentiable. I mean in X, right? Of course. And gfx, right? It's Gâteaux. Oops. Derivative at X. Okay, so and finally we define the Fréchet differentiability. So if additionally, the limit, so probably I will not write the limit, but I will just write the short notation. If the norm of f of x was h, right, minus f of x minus, the Gâteaux differential of f at x applied to h, right? If this, probably, let me put it in bracket, right? Because the fx is actually a map. So if this norm here, shift it a bit, oops. So if this norm here is actually small o of the norm of h in x, right? For norm of h in x actually going to 0, then f is called Fréchet differentiable in x, right? And let me just arrange this bracket here. Good. And f prime of x, right, which we define to be df x, right, which is actually a linear bounded operator, right? It's actually it's Fréchet. Oops, I wanted to change the color. So this will be its Fréchet derivative. Okay, so if furthermore the map, if furthermore the map which at x associate f prime of x, right, is Lipschitz. The map is Lipschitz continuous. It's Lipschitz or continuous, right? Then we call f Lipschitz. And we say that f is actually Lipschitz, respectively continuously differentiable. So, so for Fréchet differentiability, you need that the function is, should be Gâteaux differentiable, and this condition here should be met, right? So, okay, so now I claim that I think it's already quite obvious that if you have a function that is, so I claim that Fréchet differentiability implies Gâteaux differentiability. Right, it is kind of obvious, right? Okay, so but actually, as some of you know already, right, the reverse is not true, right? If you have a function that is Gâteaux differentiable, that function is not necessarily Fréchet differentiable. You can actually find, you can construct a very kind of can easily construct a counterexample, right? So I leave it to you, right? So you can, you can suggest some counterexample of a function that is Gâteaux differentiable, but not Fréchet differentiable. So put it in the comment below, and yeah, I will check your answer. Okay, so of course, if you, let's write also some basic property. So if f and j, right, are defined from x to y, right, are directionally differentiable, then the sum is also Fréchet differentiable, right? It's directionally differentiable, sorry. So let me just check something, right? I have the feeling that I did a mistake somewhere. Okay, no. I had the feeling that I directionally differentiable with only one L. But that's not actually the case, right? So everything is fine. So if you have two functions, f and j, right, defined from x into y, right, not from x to y, that are directionally differentiable, then the sum is also directionally differentiable, right? And you can even write the directional derivative, right, of the sum as the sum of the directional derivative. Oops. Right, and this of course holds for every x in x, and for every direction h in x. Okay, so for Fréchet differentiable operators, we also have the following chain rule that we encapsulated into theorem 2.5. So let change the color. So let x, y, and z, right, be Banach spaces. Right, and let say you have a function f, right, defined from x into y, right, be Fréchet differentiable in x, in capital X, right, and the function g, right, is defined from y to z, right, be Fréchet differentiable in y, right, which is actually the image of x via f in y. So let me just highlight our assumption, right? So you have Banach spaces, you have differentiability of f in x, and then you also have Fréchet differentiability of the function g in y equal f of x, right? So in this case, then the composition g composed with f actually is Fréchet differentiable in x, right? And we have the following chain rule, that you know, right? Nothing new. G composed with f prime at x is actually g prime at f of x, right? Composed with f prime at x, right? Because those are maps. Okay, so if you have these assumptions here, then you can conclude about the Fréchet differentiability of the composition of those operators. And again, let me just hammer this, right? Let me stress this fact here. G should be differentiable in y equal f of x, right? Otherwise, you have a problem. Okay, so let's go into the proof, right? I think we are not going to prove it, right? The proof, I leave it to you, right? We will not go to the proof, right? Into the proof, because it is actually, it is exactly as in the finite dimensional case, right? So I will leave it to you, and of course, if you face any problem, feel free to drop your query in the comment below. And I will be happy to assist you. Okay, so however, let's have a warning, right? Because so try it out. It's not difficult. So however, let's have a warning. Oops. Okay, let me just style it a bit. Good. And probably let me just use this color, probably. Okay. Okay, so looks quite nice. Let's have a warning. Actually, what I want to say is that a similar rule for Gâteaux differentiability, for Gâteaux derivatives, to cut it short, does not hold. Right? If you have function f, right, defined from x into y, right? Gâteaux differentiable, right? In x, right? Capital X. And you have the function g, right, defined from y into z, also Gâteaux differentiable. In y equal f of x, right? It's an element of capital Y. Then the composition, right, does not need to be, it's an S here, right? Need not be Gâteaux differentiable in X. So for this to hold, one need probably I use another color. Maybe change the color just for this. So for this to hold, for this to hold, one need the function f, right, to be Fréchet differentiable in x, and you can actually prove it, right? So I strongly invite you to prove it, right? And of course, feel free to drop comment, right, about how you can go about the proof or anything, right? So if you face any problem, any issue, please reach out to me, right? And I'll be happy to assist you. Okay, so we also need to, the following variant of the mean value theorem, right? That will be very, very useful at some point in this lecture series. So this is actually given by theorem 2.6. So say this is a variant of the mean value theorem. So theorem 2.6. Okay, so let f, right, define from an open subset U of x, right, to y, right, be Fréchet differentiable and let x in U, right, and h be a direction in x. Assume that those are given, right, such that you also need to make sure that x plus th is actually a feasible direction, so that this sum is actually in U for every in 0, 1, right? Then, so before we proceed, let me just highlight f should be Fréchet differentiable, right? And also we need to make sure that the x plus th is actually a feasible direction. Okay, so if you have this assumption, so I think I forgot something. This U should be open, right? So, okay, so if you have a Fréchet differentiable function, right, and then you have an element x in U and a direction h, right, such that x plus th is also a feasible direction, then f of x plus h, right, minus f of x, right, it's exactly the integral from 0 to 1 of f prime of x plus th applied to h, right, dt. Okay, so nothing new. It looks similar to the mean value theorem that you know. So for the proof, so let's go into the proof, right? I'm just going to give you the proof idea, right? So this is not the full proof, but I strongly invite you to, to write it kind of, to write every step of the proof, right, on your own. And of course, if you have any problem, feel free to reach out to me, right? Feel free to reach out to the community, right? Because we are here to support each other and really, help each other reaching another level in his understanding of mathematics. So for the proof, define another function f, right, an auxiliary function f from 0, 1 to r, right, which maps t to the duality pairing, right, of say psi, f of x plus th, right. This is the duality pairing in w star, w in the dual space of y. I said w, but it is actually y, sorry. So the function f maps t to the duality pairing between psi and f of x plus th, right? Because this is an element of, this is a linear bounded operator, right? And this is an element of y, right? So this is well defined. So of course, this is actually for an arbitrary psi in y star. So if you put this, if you define this function small f, then the next thing for you to do is actually to use the fundamental theorem of calculus in R, right, to conclude. So this will be kind of the proof idea, right? How you can prove the mean value, the variant of the mean value theorem when dealing with infinite dimensional spaces, right? Okay. Of course, if you have any problem, feel free to reach out, right? It will be very, I will be very happy to help you. Let's have a look at some important special cases. So just write the important special case. Just put case, right? Or maybe cases, right? No case, right? Because this is only one case. So the important special case actually when the codomain is actually R, right? So when y equals to R, which is of particular relevance into optimization, right? So we can have, we have then function f, right, that is defined from x into R, right? So if the function f is Gâteaux differentiable, at x, then the Gâteaux derivative at x is actually, a linear bounded in the dual space of x, right? I think this is quite obvious, right? It follows from the definition, so nothing really special. So the second case scenario is that if x is a Hilbert space, so if x is a Hilbert space, then there exists we call it gradient of f at x, right, in x, such that this dual pairing, right, dfx, 8, right, in x star, x, right, is exactly equal to the scalar product of these two things in x, right? This is actually a consequence of the Ries representation theorem. So this is Ries representation. Okay, so before we proceed, I strongly recommend you, checking out my lecture series on functional analysis, right? As we delve into non-smooth optimization, you will find that the concept we discuss or will discuss tie back to the foundations we covered in the functional analysis lecture series. So trust me, it's actually a journey worth taking. So check it out. Okay, so another remark, another point is that the Gâteaux derivative, right, of f at x is actually a linear bounded operator, right? So this is, the derivative of f at x. This is a linear bounded operator, but the gradient, right? We use the same color. The gradient of f at x actually is an element of x, actually, right? This by the Ray's representation theorem. So what I want you to observe here is that the gradient actually says strong topology on x, right? As being an element of x. While derivative does not. Right, so an instructive example to kind of hammer this fact is the following, right? So let's have a look at this example, just to showcase the fact that gradient is strong topology on the space X, but the derivative does not. Okay, say you have let say X, right, and go with this scalar product, right? So let X with this scalar product be a Hilbert space. If you don't know what a Hilbert space is, then again, I have my lecture series on functional analysis, so check it out. So let X be a Hilbert space, right? And say you have M, right, a linear bounded operator, defined from X into itself, right, be a self-adjoint positive definite operator, right? Because M is actually a self-adjoint positive definite operator, it is invertible. So let me just write it here. And there's continuously invertible. Continuously. Invertible. Again, as I said, functional analysis is actually kind of one of the cornerstone of mathematics, right? So again, in my lecture series on functional analysis, I went through the spectral theory, right? We went through self-adjoint compact operators and all of those stuff. So, I think you won't really regret, right? So check my videos out and, and then I think you will definitely learn a lot from those videos. So let X be a Hilbert space and M be a linear bounded operator, a self-adjoint positive definite operator, right? Then the new scalar product, right? Say I put here Z, right? This new scalar product that I define to be the scalar product of X and My in X, right? So I said scalar product, but I wanted to say that this new operator here actually defines an inner product, like scalar product, an inner product on the space X side, and induces an equivalent norm that we call, defined by norm of X, right, is actually this scalar product, right, space Z to the power 1 over 2. So, and this define an equivalent norm on X, right? So please check it out, right? And check it. Check that this operator here, defined like this, defines an equivalent norm on the space X. So because of that, we can conclude that hence X endowed with that new scalar product. So we just write, the dot is just a placeholder, right? So X endowed with this new scalar product, like, is a Hilbert space. If you are lost about this, so just know that, oops, good. Just know that this is this scalar product that I call Z. So this X defined with this new scalar product is a Hilbert space as well, right? So now consider, so we have a space, right, that you can endow with two different scalar products, but different scalar products, not really different, but they define equivalent norms, right, on the space X. Now consider the function f defined from the space X endowed with the usual, the usual scalar product on X, right, into R, and say f tilde is actually defined on the same space, but this time with the new scalar product into R. So consider these two functionals, right, defined by f of x, right, equals f of f tilde of x, right, which is exactly 1/2 of the norm of x in x, right, say squared, of course, for every x in x, right. Well, this function is well defined, right, since norm of x is an equivalent norm on, on this space, right. So then, if you kind of compute the Gâteaux differential of this functional, then you get that the Gâteaux derivative of f at x applied to h, it's exactly it's the same as the Gâteaux differential, the Gâteaux derivative of f tilde at x applied to h, right, which is exactly this scalar product in x, right, and this of course for all h in x. Okay, so this is clear, right? So just I think this is okay, right? How we can derive the Gâteaux differential, so we can just apply the definition. Okay, so however, the gradient f tilde, the gradient of f tilde applied to x, right, is now characterized by we should have this. This is actually the derivative, right? This the derivative of f tilde. So that this is equal to this, right? So let me just write it here even. So this is actually this dual pairing, right, in x star comma x, right? So by the raised representation, right, this should be equal to the gradient of f tilde at x, right, the scalar product of this gradient, but in the space, this for this scalar product z, right? The scalar product z is exactly this scalar product here. And this is of course for every h in x. So from this, actually, so from this relation here, you see that this term here should coincide with this term. You can pull, you can bring this one on the other side, right, and then see that this equals to 0 for every h. So this means that the term here, minus this term here should actually equal to 0, right? So from this equality here, we see that the gradient of f at x should be equal to the inverse of this function applied to x, right? The inverse of m applied to x. So this means that the gradient of f at x tilde, right, which is equal to m minus 1 applied to x, right, is totally different from the gradient of the function f at x, which is equal to x, right? So the gradient actually, strongly depends on the inner product on x. So this is actually the morality of this thing, right? So what you should keep in mind. So let me just write it. So the gradient strongly depends on the inner product. On the space X, right? Because remember what we did. What we did is that we actually, we picked actually two functions, right? That are kind of equals. So f of x is equal to f tilde of x, right? So their derivative coincide, right? So this, the derivative coincide, right? But the gradient actually differ, right? And this is exactly what I was saying. Gradient actually says strong topology on x, right? So it heavily depends on the topology associated to the space X, right? And because here we are dealing with Hilbert spaces, you can talk about scalar product. So that's why the conclusion here is that gradient strongly depends on the inner product on X. So it depends on the topology, right, that you put on the space X, and the strong topology on X. Okay, so I hope this is clear, right? So now we now turn to characterization of minimizer of a differentiable function f. So maybe so now just keep it short, right? Now we turn to the characterization of minimizers of a differentiable function f. Say f is defined from x into r is differentiable, right? And then again we are interested into, as I said, want to get the element x that minimizes the functional f. Well, we know that an element x bar, right, in x is a minimizer. Is a minimizer of the function f, right? If and only if. Let me just write I double f for if and only if. If only if f of x bar is actually also equal than f of x for all x in x, right? But the problem here is that this is practically not useful at all, right? So we need to characterize x bar beyond this, right? This is actually not useful. Even if I give you x bar, right, which is indeed the minimizer, and I ask you to check whether that x bar is actually a minimizer, you cannot apply this. You cannot take this property because this space here is actually, infinite dimensional. So you cannot actually check for all. How would you do that actually? So we need to characterize x bar, minimizer beyond this property here. And this will be done via the Fermat principle, right? Which will be our subject of concern in the next video. So stay tuned for that, and don't forget to subscribe to the channel, and I really look forward to welcoming more subscribers, right, to the channel next time. So I count on you to share the video or the link of the channel, right, to friends and relatives, anyone interested into advanced mathematics. So, you can even do it as follow, right? Share the link share the link of the channel to 3 people of your neighborhood, right? That we share it to 3 people of your neighborhood, and so on. That's actually the only way we can actually spread the word, right? So, having said that, thank you in advance for your support, right? And until then, happy learning, and see you in the next video.